Welcome, soil conservation and management students from the Royal University of Agriculture. This is our session 14 lecture series on global navigation satellite systems and geographic information systems, and this is video lecture 14-4, or video lecture number 4, where we're going to focus on GNSS errors and sources and corrections. So what causes error in the signal? As you've probably used your phone to navigate on the roads and have it sometimes take you the wrong way or put you on the wrong road. What's the error? What's causing the error in those systems, and how do we correct those? Okay, and so this is a part of our lecture series on global GNSS and GIS, and specifically in the past we talked about how GNS works and its different components. Now let's talk about some of the error sources and the way we correct it. Okay, so here's there are 4 different types of error common to a GNS system. Okay, and you can see from this image that I have here, we've already talked about how we use 4 satellites. We look at where those 4 satellites all intercept in order to try and determine our location. But the truth is, where are we standing in all of this? And you notice that there's a range around where these satellites are. So the satellites are up here in space, but their signal traveling could be anywhere within this. Oops, didn't mean to do that. Within this range here, okay. And so what the satellites kind of do is they look at, okay, what's the average location between all these satellites? But why the error? Why this error? And there are 4 different points that we're going to talk about. We're going to talk about dilution, or what we call dilution of precision, satellite visibility and narrow angles, atmospheric interference, and then something we call multipathing. So let's talk about each of those. The first one we have is GPS error. For GPS error is poor satellite visibility, or narrow angles. And so here in the center is our good signal. And if you notice, we have 4 satellites and they're spread out. Okay, they're in different positions above the sky. Some are a little higher, some are a little lower, but we have a mix. That's good. That's what we want. But in this here, where we say poor satellites, poor precision, notice that all the satellites are up above us. They're up there. Okay, they're up above us. And so that narrow angle allows for more error. Okay, and so that's not good. And sometimes we may have lots of satellites above us, but because of structures like buildings, okay, so we have a building here, buildings or mountains, okay, that might block the signal. And you have to have what we call line of sight. There can't be anything between us and the satellite. Vegetation is okay, but there can't be buildings or mountains between us. They block the signal. In other words, the signal comes down and bounces away. Okay, it comes down to this mountain and bounces away, and it doesn't get to us. The result is that we only get satellites that are like we had here in this first example. They're just above us. Draw a few more satellites up here, but they're right above us, and so we have that narrow angle issue. Oops, sorry. We have this narrow angle with only satellites being above us, okay, as well as there's not as many satellites, and so it increases the amount of error in calculating our position on Earth. Okay. A second one that we mentioned is atmospheric interference. Okay, what the atmosphere does. And that's because in the atmosphere, okay, there are some charged particles. So there's some sarat down in pantok, okay, and the pantok kisanid. And these particles, right, like cations or anions, cation and anion, okay, these particles in the atmosphere, okay, will cause the signal to bend. So we have 2 parts of the atmosphere, one called the ionosphere and another one called the troposphere, that have these charged particles. Okay. basically, again, Anyon and Kachong in them. And so what happens is the signal, as you can see here in this picture, as the signal comes through this ionosphere, notice that it moves around some. Remember, we're measuring, in order to get our GPS accuracy, we're measuring how long it takes, or the distance from this satellite to where we're located. And if that signal comes in and then bounces around some, it travels a greater distance than if it traveled straight to us. Okay? And so that will also cause some error. The next one we have is called multipathing. Okay, multipathing, this is what happens when GPS signals bounce off of buildings. Okay, so for example, here's our drone or our GPS. It happens to be a drone with a GPS on it. The direct or correct signal from the satellite is that signal that comes straight down here to it. But what happens is that signal right from the satellite is coming out in this kind of a fashion. And so some of that travels down here and it hits this building and bounces off at an angle. Again, that path is traveled further than the direct path, and that causes some error to occur. Okay, so that causes some error. And so that multipathing causes some problems. The GPS signal doesn't travel straight, it travels down, bounces off, and comes in on us. And so that can really cause it to jump. And if you've ever used a GPS system, maybe when you're in Phnom Penh and you're driving between the tall buildings in Phnom Penh, it will jump streets. It'll change the streets you're on as you're driving because of that multipathing. Okay? Okay. And so let's talk about some ways that those signals can be corrected. I should mention before we talk about these correction systems that there are also there's also error sometimes in GPS caused by the government. In other words, the government will change the signal typically because of war or national security, and change the signal and have error. Okay, and that's this one back here. The first one we talked about, it's called dilution of precision, and that's when government or military causes error. Okay, and that's only done for security or war. Okay, let's think about ways we correct this. So how do we correct that signal and make it accurate? Okay, and the systems that we use to do that are what we call real-time systems, or differential GNSS, differential. Okay, and let me explain how that works. Okay, so if you look at our image here, we have our user. So here's your GPS receiver here that you're using. That could be, again, be your smartphone. And so we know there can be some error from what we just talked about. So what we do is we have what we call a differential station. Sometimes these can be called a base station. Okay? And it's permanent. It's a permanent station. And what we've done is we know its exact location. So we know it's exact. So the base station, we know it's exact / accurate location. Okay, so we know its location. And then, just like our receiver, it's calculating its GPS or its GNSS location. So then it calculates GNSS location. Now, the word differential comes from the word difference, right? The word difference. Okay, so it's got its exact location here on the Earth that's surveyed, and it's calculating its GPS position or its GNSS location. Okay, and then what it does is it calculates the difference, right? The word difference. What's the difference between its exact location and the location it has based on the satellites? Okay, so it has its exact known location, okay, and it calculates and it knows its position from the satellites. And what's the difference? Okay, and it sends that difference, okay, what we call differential. So the differential, that's a noun for the word difference. Differential, it sends that differential via data to your GPS receiver, which then adjusts or adjusts or corrects your location based off of the difference. Okay, so the base station calculates the difference between its known location and its GNSS location, sends that to your receiver, and then your receiver adjusts accordingly. And that's because the error that's experienced here, okay, this difference should be similar to that if you're within, say, a couple, maybe 200-300 kilometers. The difference would be very similar. And so what a differential system does is if you just use straight GPS, your accuracy would be about 100 meters. But if we use differential correction, we can change that to 0.05 to about 8 meters, depending on the type. There are different types of differential GPS, and depending on which type we use, we could be accurate to 5 centimeters or within 8 meters. Most of the time, we're somewhere between 1 and 3 meters. Most of the time, like your phone, your smartphone, I have my smartphone here, it's going to be accurate to within 1 to 3 meters because it's using a differential system. Okay? And there are some different types of differential systems. I'll give you some examples of some differential systems. One that's used in the United States is called a Wide Area Augmentation System, or WAAS. Okay? A Wide Area Augmentation System, WAAS, WAAS. And again, it makes our accuracy less than 3 meters. And so the way that works is across the United States there are those base stations, or those differential stations. You can see them listed, see them here on the map of the U.S., right? You have these correction differential stations. And what they do is they send their differential information up to a satellite, and then the satellite broadcasts that down to you as a user here. Here I am standing using my GPS, and here's my GPS, and so it broadcasts that signal to my GPS, corrects it. And what it does is, based on my location, my GPS grabs or receives the signal, and then uses the signal or the differential from the nearest differential station. Okay? And so again, my GPS is calculating its location and then shifting or changing that position based off of the differential at the base station. Okay? So this is the most common type of system. You have base station, it sends a signal up to the satellite, which is then broadcast out to your GPS. And then your GPS calculates its position, takes the differential, and corrects. Okay? Another system is called real-time kinematic, or RTK GPS. And RTK GPS works essentially the same way, with the exception of how the base station works. There's our base station. Okay? This time we set up our base station. So we survey our base station into a known location, okay? And then it gets its differential signal. So it calculates differential here. I guess it's down here. This calculates the difference, or the differential. Okay? Calculates the differential. And then it sends that differential from the base to what we call the rover. And the rover is you, the user. Okay? Now these systems are not open systems. They're only available to those that own it and are using it. But you can buy your own system. In fact, at my home university, Brigham Young University, Idaho, we have this system that we use with our tractors. We bought it and we use this system. Okay. Anyway, you can see here. Here's our base station, and here's our rover. And so what happens is, again, it works the same way. Okay. Our signal comes down here. It calculates the differential, and then it sends that differential to me, the rover. And because the proximity of these are very close, okay, so about 50 kilometers or less, it is much more accurate. Okay, In fact, an RTK system has about 2 to 5 centimeter accuracy if it is set up correctly. In fact, here is a list of different types of systems and their accuracy. The original GPS system, 100 meters. A GPS system today with some improvement is 15 meters. If we have differential GPS, like what we talked about today, we have 3 to 5 meters and maybe is less than 3 meters. RTK, less than 10 centimeter accuracy. Okay, so there are some ways that we can make it more accurate. It can make it much more accurate than your phone. And for some of our agricultural operations, these systems, our differential systems, are very accurate. If we're using auto steer, tractors that drive themselves, then we need RTK. We need this accuracy for auto steer. Okay? So again, these systems are used in agriculture and work. That concludes this video lecture number 4 from session number 14.